Today we're going to start the second half of the course, which is the analysis part. We have finished design. We have studied 3 design techniques to solve problems, namely divide and conquer, greedy, and dynamic programming. And from now on till the 11th lecture, we're going to cover analysis techniques that you could use to understand the performance of any given algorithm. So let's start. We're going to study the following techniques. We're going to study first the topic of asymptotic analysis, the notion of the O that you have learned in CS3, perhaps even since CS2 days. What does it mean? What's its significance? And why are we doing it that way? And next, we're going to study a number of techniques for analyzing iterative code. We will see also today the notion of using summations to derive the O of a piece of code, the big O of a piece of code. We will also look at amortized and randomized analysis, and these are special techniques that you use when an algorithm is either doing amortization. In this case, you're going to do amortized analysis, and we'll talk about what does that mean later on, or is invoking some random process, like generating a number between 1 and 100, and based on the output of that process, doing something. So for that, we will learn a topic called randomized analysis, where you talk about the performance of the algorithm in a probabilistic sense. And then we will see 3 also techniques for analyzing recursive code. These are recurrence trees, master method, and a theory called the acrobacy theory. So we have a lot of things to cover. And by the way, by covering all of these topics, there is nothing left for you to learn to be able to analyze any piece of code. So I'm giving you all the techniques that exist in the computer science theory area to be able to analyze any algorithm or any piece of code. Let's start first by asymptotic analysis. You were introduced to this topic early on in your computer science education, but you were given a common sense, intuitive way of thinking of it. What we will do today is define it formally and understand where is all this coming from, why, and what are the variations of notations we have to talk about the performance of code. What's the problem? What we are trying to do, what we are after, is to quantify the performance of an algorithm. Any algorithm, given an input, should produce some output. It takes time to do that. So it makes sense to measure the time it takes an algorithm to solve a problem, to produce an output. However, algorithms are, if you'd like, a special kind of machine. They're not like regular machines. Regular machines have fixed set of components. I mean by regular machines like a physical machine in a factory. It has a fixed set of components. So the running time of a specific machine will always be the same. If it delays in executing a task, that often refers to a hardware failure within the machine. But software is not like that at all. Software is intelligent. And what that means is that there are different pieces of code that might be executed whenever you pass some input because of the nature of the input. So there could be blocks of code that don't execute between one run and the other. What that means is the time will vary, not because there is some kind of failure, but because of the nature of the input. Now, also, the same program running on different machines with the same input, although will produce the same output, but it will take different amounts of time. The reason why it's taking different amounts of time is because of the capabilities of the hardware. Again, with physical machines, we don't have this multi-layered architecture where we put the software on the top of the hardware. There's just one thing, which is the hardware. Now, in the case of software, the performance of a specific algorithm could be enhanced by just changing the hardware. So if you try to time it, the value that you get from the clock that you have used to time is only meaningful in the context of the hardware that you've used. So if you run on a quad-core 2.8 gigahertz processor for some big input, a specific algorithm, and you measure the time and it takes 3 seconds to execute the desired functionality and produce an output, now you go to a quad-core of 3.8 gigahertz, and instead of 2 seconds, you get 1 second, or you get 1.2 seconds. And if you run it on a slow processor, like a Pentium, maybe it will take 6 seconds. So the notion of time does not really reflect how good an algorithm is, because it encompasses in its measurement the speed of the hardware. And it's not just the speed of the hardware, it's even the OS, what is the OS is doing all the time, which is context switching between processes and utilizing virtual memory sometimes versus utilizing physical memory other times, will affect the performance. What that means is that computer scientists from the early days realized, with the continuous improvement in hardware and OS, that timing, or measuring the time, is not that useful. It's not really representative because it is not generic enough. It cannot be applied to all machines. The value that you get of measuring a piece of code on a specific hardware will not necessarily be reproduced on any other hardware or on any other OS configuration. And that created a problem, because when you talk about performance, you would like to refer to time. This is how we think, this is how what we believe, this is how we were taught since we were young. You know, we would like to time things. If I talk about performance, if I ask how fast is the car, the answer is, you know, the car accelerates from 0 to 100 kilometers in X seconds. Okay, that's why people pay for a Porsche or a Ferrari, because of the significance in the reduction of time. So time is, for us, the meaningful and logical way to measure things, but it just fails when it comes to software. Now add to that for any given algorithm, there are really 3 different running times or cases, if you'd like. So even if you fix the hardware and you fix the operating system configuration, you're going to still get 3 cases. A case where the algorithm runs as fast as possible, as it can, and a case where it runs very slow, and an average case in the middle. And this is only in software. If you think of any other physical machine, it doesn't work like this. You know, the machine performance is constant and it's limited by mechanical factors. If you think of your car, for example, you know, it is not acceptable that one day your car, while you're coming to university, will just be slow, and the next day it's going to be fast, and the third day is going to be average in between fast and slow. Okay, in software, that's the case all the time. For any given algorithm, we can think of a case where the algorithm will run in what we call the best case, which is the fastest performance, and there is a case where the performance of the algorithm degrades, so we will call it the worst case, and there is the average case as well. And the difference between best and average and worst could be really huge. Okay, so that's another layer of complexity, if you'd like. You know, apart from the fact that the performance will change from hardware to hardware, performance will change from operating system to operating system. Even if we fix the hardware and the operating system, we still run into this issue of we can't talk about it in one way. There are really 3 cases we have to consider for any given algorithm. So as an example, if you we call simple linear search, an array that you're given and you would like to find a value in the array. Okay, for example, the smallest number. Now, if the array is sorted, the smallest number will be in the first cell. And if you're doing linear search, which is a simple for loop, and inside it there's a single if statement, then your best case is you find the entry in the first cell. The worst case is that you're looking for the largest value, or you're still looking for the smallest value, but the array is sorted in reverse, so you will find it in the last cell. And for the average case, you'll find it somewhere in the middle. Okay. Now this is applicable from linear search to even the more complex algorithms, to even the most complex algorithms you can imagine. You can always think of 3 cases for any given algorithm. The question is the performance the same in the 3 cases? And we will talk about that later on. Now again, just to motivate the idea, if you think of a sorting algorithm, any sorting algorithm, best case for a sorting algorithm is the data is sorted. So in most of the cases, there are no swaps of values within the array of values to enforce the sorting, because it is already sorted. The worst case is that it is sorted in reverse. So every single value will move from its place to some final destination, which is not the location it is in. Okay? And in the average case, half the array is sorted and the other half is not sorted. So half the values will stay in their place and the other half will move around. Okay? Now, if you have never been taught the big O notation, and I tell you how to solve the problem that we are facing, how to measure the performance of an algorithm, you will most likely come with this scenario. You will tell me, okay, I will implement the software. So instead of being an algorithmic description of how to do something, I will actually implement it. And I will create different data sets. And I will get access to as many machines as I can, as many computers as I can. And I will install on them different variations of operating systems. And I will measure the time of running an algorithm for each one of my different inputs on each one of my machines and on each one of my OS configurations. And then at the end, I will look at the values I have calculated or measured, and I will compute the mean or the average. And, or perhaps if you are a little bit more into math, you will tell me, I will plot the points for every input size, the average on all machines and all OS configurations. And then I will draw a line across these points. And this line will describe the average performance. Okay? So you basically give me a curve. You tell me, okay, it's behaving like this. Well, both techniques are actually not entirely wrong, but they have problems. What are the problems? Well, first of all, you have to implement the software. Okay, so for any given algorithm, you cannot start to talk about it. Let's say you get an algorithm idea. You cannot start to talk about it unless you implement it, because you're going to implement it to be able to measure it. The second thing is, your results are only limited to the machines and OS configurations that you've tested on. So if any new machine or any new version of an operating system is released, you will have to go and redo your tests, which doesn't make sense. It is too time consuming. It is an inefficient process that you're going through to be able to talk about the performance of a single algorithm, because you really don't know the changes in the operating system architecture or the introduction of a new hardware architecture. Like historically, for example, we didn't have quad cores. We only had single core. Okay? Now with the introduction of quad cores, the way programs run are completely different. So you will have to redo the tests. So it's quite a limited approach to thinking about understanding the performance of an algorithm. And you might ask, okay, nobody's doing this, and I tell you, actually, no, there are a group in computer science that will do what I'm describing, which is the measurement, which is the systems research area. Systems are those who research in operating systems, including desktop operating system and embedded operating systems and so on real-time operating systems. They do such kind of measurements, and they report it and they publish it in research papers. But they are an exception because usually they work with a very constrained environment, so they don't really consider general purpose operating systems running with tons of applications. Instead, they would say develop a new algorithm to do scheduling on a real-time operating system that would be used in airplanes. So they set it up so that it's a replica of what exists in a specific real-time operating system on the machine, and they do the measurements and they publish the findings and so on. But if we're talking about the performance of any algorithm for to be used anywhere, then this technique really is tedious and it will take time. Now, so this is what I was just mentioning, that limitations of experimentation. What I'm describing is called experimentation in the systems research area. Experimentation is limited because it is difficult in the sense that it requires you, whenever you think of any algorithm, to implement it. And second, it's only representative of the hardware configuration and the operating system configuration that you have used. And third, which is also an important point, you can talk about two algorithms, which one is better, unless you run the two algorithms on the same configuration of hardware and operating system. So that means if you're given a choice to pick between 5 algorithms, you'll have to implement the 5 and test the 5 on the same set of machines and operating system configurations to figure out which one is better. Now obviously this is too much. This is a hassle, because we in software development, on a daily basis, a developer would be facing the choice which algorithm to use. So we need a more pragmatic, simpler way to actually talk about the performance of algorithms. Now, so here is the idea that was introduced to you in CS2 and CS3 days. The idea goes like this. We're not going to measure time. Instead, we're going to talk about the performance of an algorithm in terms of the size of the input data. So it's not in terms of time, it is in terms of the size of the input data. The idea was intuitively introduced to you as follows. The amount of work that the algorithm performs in relation to the size of the input, which we're going to call it n. So if I'm giving you an algorithm that takes n and will do n steps, we will call it an O of n. And if I give you another algorithm that accepts n as input and it's going to do n cubed steps inside it, then we're going to call it n cubed. So even though it's taking n input, it is doing n cubed steps. So I'm talking about the number of steps within the algorithm, the number of decisions within the algorithms. And we will refine this concept later on in detail. But I'm talking about the number of steps in terms of the size of the input, not the size of the output, the size of the input. Okay? Now, the nice thing about this, there is no notion of time. We're just referring to the number of steps. And whether you put the algorithm on a quad-core 3.8 gigahertz or a quad-core 1.6 gigahertz or a Pentium Celeron 1.4 gigahertz, the number of steps is always the same because it's the same algorithm, it's the same piece of code, so the number of steps is the same. Now, on different hardware configurations and on different OS configurations, the number of steps might run faster, but it doesn't matter because we're not talking about time. So we're really referring to it in terms of the number of steps, and that's it. Okay? Now, this was an ingenious idea in the history of computer science because it solved a very complex problem, which is how to talk about the performance of an algorithm without referring to the underlying hardware or the underlying operating systems and without talking about time, without mentioning the word seconds. Okay? So this was the intuitive idea behind it. This is what was introduced to you in early days, okay? That we're going to use the word O of n to relate the steps to the input size. Now, the number of actual steps done by a specific algorithm could be anything. It could be like, 5n squared plus 23n plus 94, or it could be 16n plus 59 log n. It could be anything. So if it was kept as an idea that we are going to spell out the number of steps in terms of n, and it was kept open for developers how to express the performance, or how to determine the performance of an algorithm in terms of n, then we would have seen very long formulas, and that would again have introduced a level of complexity that we're trying to shy away from. I don't want to be in a position where someone tells me, what's the performance of an algorithm, so I tell him, okay, it's going to be 96n cubed plus 27n squared plus 103n plus 77. Okay, it's just too much. Okay, when I say 77n cubed plus 15n squared plus 15n, well, n cubed is much bigger than n squared, and it's much bigger than n, so isn't it enough I would just say n cubed? Okay, although the word n cubed is not entirely correct, because it's really not just n cubed. There is an n squared term there, and there is an n term there, and there's a constant term there. But computer scientists figure out from using simple mathematical knowledge that if you look at n cubed and you look at n squared and you look at n cubed is much bigger, and if I'm after a general characterization of the performance of an algorithm, I'm just going to talk about it as n cubed, even though there are other terms. I will pick the biggest power and just talk about it in that terms. Okay, while they were doing this simplification, which appears for the first instance that it's not a good idea, it's not accurate, it's inaccurate, because it's not n cubed, it's n cubed plus n squared plus n. And the answer is, well, it doesn't really matter, because as you go to infinity, n cubed dominates. Okay, if you keep plugging in actual values for n and you keep increasing them, ultimately the contribution coming from n cubed is so huge compared to the rest that really n cubed is making up the result. And for that reason, they adopted a basic family of curves that we all know and we have studied in calculus, and this is the one that shows up in this slide. This is what we use to talk about the performance of algorithms. Okay, so each one of those, don't think of it as a specific curve, it's a family of curves. Okay, so there's the family of constant curves. 5 is a constant, 6 is a constant, 100 is a constant, a million is a constant. So when we talk about the performance of an algorithm being constant, it doesn't mean that it's 1. Okay? It means it is some constant number that doesn't change. When we talk about an algorithm being log n, it doesn't mean it's exactly log n. Okay? It could be like 100 log n, or 70 log n, or 1 million log n, but it's still log n for us. Okay? When we talk about the performance being n, it doesn't mean it's exactly n. It could be 700n. It could be 30n. Okay? Now, but n is quite different from n log n, and quite different from log n, and quite different from n squared, and 2 to the n is quite different from n cubed. So each one of those is a family of a huge number of curves that you might see when you analyze. But it doesn't matter. It's a simplification that we make to make the expression that we use to talk about a specific algorithm performance as simple as possible. So developers can talk fast about the performance of an algorithm. you look at a new algorithm, and what you really want to see is just a simple term that tells you what is this, okay? You want to know is this is 2 to the n, which means you should avoid it, or is it n log n, which means you should look at it, okay? Whether it's, 177 2 to the n or 93 n log n, it doesn't matter. This is n 2 to the n and the other one is n log n, okay? So what happened in the early days of computer science is that they adopted these basic mathematical curves, and they said actually we're going to use them when we talk about performance. And instead of bringing up a long formula that describes the number of steps, I'm just going to use one of those guys. And this is the idea here. Now each one of those, if you remember from your calculus days, is quite a different curve. I mean by that, if you plot all of them on the same chart or on the same page, and you keep plotting till infinity, they will never intersect, okay? After a point, they will never intersect, because their behavior is quite independent from any of the other ones. And this notion that they don't intersect is interesting. This is really what made computer scientists from the early days say, okay, we're going to use these curves to talk about performance, okay? Because we don't really get too excited about small input. The problem will always appear in an algorithm as the size of the data keeps growing. And since there is a point after which these guys will never intersect, then when we talk about them, we are talking about the performance of the algorithm on the long run, as it keeps getting different inputs and larger inputs. And generally the tendency for any algorithm when it's running, that the input to it will keep increasing as as time passes. Okay, if you think of the algorithm, for example, in your contacts app on the phone, when you buy the phone and it's your first ever phone, now you get like 1 or 2 contacts, your mom and dad, and then as you keep meeting people, you keep collecting numbers. So the input to the contacts app, and perhaps this, if you'd like to think specifically to the sorting app in the sorting algorithm in the contacts app on your cell phone, the input whenever you would like to sort the numbers, the names, will keep increasing. So we're interested in the behavior of the algorithm as time passes, because we will see more input. So we're generally interested in the behavior as the input goes to infinity. And as these curves go to infinity, they will not intersect. So I am confident when I say 2 to the n that it's going to be really horrible. Okay, it would never drop and become like 0. Okay, unless I'm multiplying by a constant that's a 0, which doesn't make sense. Now you might still be thinking of improvement in hardware, and you tell me, yeah, but if you are saying that the number of steps is n squared on a Celeron, Pentium Celeron processor for a specific input, it might take 2 seconds for the n squared to execute the n squared steps. But if I take that and put it on a quad-core 3.8 gigahertz, the 2 seconds could be like 0.5 seconds. So isn't this representation in terms of input inaccurate because it didn't reflect, or it does not reflect, the change in time that will happen? And my answer is yes. Obviously, if you move from a Pentium processor to a quad-core 3.8 gigahertz, the performance will enhance drastically. It's not because the algorithm itself is doing something better. It's still doing the n squared steps, but the n squared steps in the first case was multiplied by some constant, because remember, it's just a family of curves, so we could be multiplying the n squared by some constant and it's still n squared. And when I moved it to the quad core, the constant became much smaller, but it is still doing n squared steps. Okay, and this is the essence of it, that the constants beside the n could change, and it will change as we change the hardware and as we change the operating system configuration. But we will still be doing n squared steps. This is the beauty actually of it. It's not a shortcoming of it. It's actually the beauty of it. It solved the problem. Okay. For me, 10n squared on the old Pentium Celeron processor and uh, 2n squared on the quad core 3.8 gigahertz is just n squared. If I'm concerned about the n squared, I should decrease the number of steps or make the algorithm smarter. So instead of being n squared, perhaps it is log n or n. I shouldn't try to change the hardware to make the program run faster. It's kind of cheating, if you'd like, in my opinion, because yeah, you can make a slow program run fast by moving it to a new hardware that is faster. But isn't it better that you enhance the performance of the slow program so that it is faster, which means it runs a smaller number of steps? That's really the real challenge for computer scientists, that you enhance the algorithm by decreasing the number of steps it takes, not by moving it to a faster computer. Of course it's going to run fast, but it's relatively fast. It's still doing n squared steps. Okay? Now, I've already mentioned this point, so I'm going to stress it again, that for us, using one of these family of curves is enough to talk about the performance. Okay? So for example, 10 squared n plus 10 to the 5 is still n. It's not exactly on the chart a line that shows up where the n shows up. Okay? As you see on the drawing here, the one in green, the solid green line is the n. It's just n. F of x equal to n. Okay? The one you learned in calculus. Now, if I'm talking about 100n plus 10 to the 5, the curve you see is actually the dotted green line. But notice as we go to infinity, the two lines are almost parallel. And they are quite different from the other one in red, which is 10 to the 5 n squared plus 10 to the 8. Just n squared is the solid red. 10 to the 5 n squared plus 10 to the 8 n is the dotted red. Now as we go to infinity, notice also that they become parallel and they are different from n. Okay, and I was describing this just briefly before, and you can inspect these curves and try it out in Excel if you like, with different number of curves, to convince yourself that the constants appearing beside the n, I mean the n or the n squared here, will not really affect the overall picture as we go to infinity. It's the same curve basically. Okay, the red solid line and the red dotted line are really the same curve as we go to infinity. There is a slight displacement because of the impact of using the constants and the n term in the red case, and even smaller displacement in the case of the green lines because of the effect of using the constants. But we will talk about them as one family, and they are indeed one family on the chart. They're quite different from the other ones. And if you plot the other ones we were talking about, the rest of the curves, again, regardless of the constant you use and the combination of terms you use, you could try like, n to the 7 plus n to the 6 plus n to the 5 plus n log n, plus some constant, and you plot it on Excel. You can simply do that as a quick exercise, and you will see it's n to the 7 at the end. It's very close, the line is very close to n to the 7, despite of having many other terms. Okay? So let's look at the theoretical formal definition of the big O. You were told in earlier courses that big O is for the worst case. So when I tell you what's the big O of this algorithm, you have to think of the worst case performance, which is executing the largest possible number of steps in an algorithm. Now, that was big O by intuition, I would say. Now let's do the formal definition of what is a big O. Remember, we are after a description, a simple description of the worst case performance. So looking at the graph to the right, what you see on the x-axis is n, the size of the input, And what you see on the y-axis is the number of steps this algorithm would take. Now, this is how we define what we call an upper bound for a specific algorithm performance. An upper bound means a worst case scenario. Let me read the definition and then we will look at the example at the bottom. It says, given functions f of n and g of n, we say that f of n is in O of g of n, so the symbol that looks like an epsilon there, we read it here as is in O of g of n, if there are positive constants c and n naught such that f of n is on the chart, on the graph, is always less than or equal this constant c multiplied by g of n for some n value greater than n naught. What does that really mean? Let's look at the example at the bottom. It says 2n plus 10. To prove that 2n plus 10 is indeed in O of n, formally, by intuition we know, yes, we told you drop the constants and think of it as O of n. But now I would like to prove it. So what I need to do is to prove that there is a variation of the n curve after some constant will always be above 2n plus 10. Let me repeat that. In order to prove that 2n plus 10 is in O of n, I have to find the variation. I mean by the variation of O of n, I mean some constant multiplied by n. So I have to find this variation of n that will always be as a curve on the chart above the line of 2n plus 10. But not always from 0, always from some point on the x-axis. I would call that point on the x-axis as n naught. So n naught is some n value after which some constant multiplied by n will always be above 2n plus 10. This is what you see on the chart. The red line is the n, but you have studied in calculus, okay? If I say f of x is equal to n, then basically any input you pass, you will get it as an output. And if you plot these numbers, if you pass a 10, you get a 10. If you pass 100, you get out and as output from the function 100. You plot it, you get this nice smooth line. Now, 2n plus 10 looks differently. It's the blue line, okay? It will change a little bit as we progress in time, but as you notice, ultimately it will be parallel to the n. So my goal is to push the n up enough so that it's always above 2n plus 10. In order to push the n up, if you think calculus-wise, I have to multiply n by constant. So instead of being n means the constant is 1. I should think of 2n or 3n or 5n or 10n and so on. Okay? Every one of those is just a variation of n. It's still n, but it's multiplied by constant, so the curve will be shifted upward. Now, I'm interested in the constant that I will multiply by n. It will cross the blue line, and this is the dashed line that you see in red. If I multiply n by 3, instead of talking about it being n, I'm just going to talk about it being 3n, which is a variation of n, which means it's still n, okay? It's O of n. If I can just use 3n as my guide, or as the goal that I'm trying to achieve, which is to bring or to draw a line on the top of the blue line, 3n is above the blue line after the value 10. Okay, and obviously if we plug in the numbers there, it should be clear why it is the case. Okay, now this is what the definition is saying. What the definition is saying, I have two functions. F of n is the computed number of steps in the algorithm in comparison to or in terms of the input size. So this is f of n. This is actually what I'm setting here to be 2n plus 10. And g of n is the asymptotic order I am interested to prove that f of n is in it. When I say is in it, it means g of n is above it. Okay, so g of n is an upper bound, it's above the f of n. Because that means f of n will never ever be worse than that. And this is the essence of big O. We're talking about worst case performance. So if I say, what's the worst case performance of this? I want to be told the term that it will never be worse than it. So I have to find the term that it will never be worse than it, and this is actually here in this context is my g of n. So it will never be worse than 3n. Okay, that's 2n plus 10. It will never be worse than 3n. Okay. So if we can prove that, we will go back to our strategy, which is dropping the constant and say, okay, yeah, instead of saying 2n plus 10 is in O of 3n, I'm just going to say it's in O of n. And they are equivalent. As I said, we're going to talk about the family of curves that belongs to, under the same label as just one. Okay, so 5 log n and log n is just log n. Log n plus 7 is just log n. Okay. Now the same thing here. Really, if I am going to be accurate, and we're not going to be accurate in that respect, I should say 2n plus 10 is in O of 3n, which means it will never be worse than 3n, and that's what you see in the graph. But I'm not going to do that. I'm just going to say it's just in O of n, and that's what the definition is allowing me to do. That I can say that f of n is in O of g of n if I find these constants. Once I find the constants, I'm going to just completely forget about them and say, well, it's just for me to prove that it's in O of n, okay, or O of g of n. Okay? So going back to the example at the bottom, how do we do it in a more systematic way? We will see a number of techniques to do that. Basically, if I would like to prove that 2n plus 10 is in O of n, what this really amounts to, I'm trying to prove that 2n plus 10 is less than or equal to some constant multiplied by n. That's what the definition is giving me. And then the rest is straightforward mathematical manipulation. I can take the 10 on one side and bring the c and n on the other side, and then I resolve with the 2n, and ultimately I find my answer, which is to pick c to be 3 and n naught is going to be 10. Okay? We will see more than one way to actually compute this, but I want you first to digest the essence of big O formulae. Okay? Now here is another example. I'm just gonna work it out with a counter example here, actually. So n squared is not in O of n. Okay? Let's actually work it algebraically first. Well, if I'm trying to prove, that n squared is in O of n, that means n squared should be less than or equal some constant multiplied by n. And obviously that's not the case. It will never have a constant. A constant is a constant. It's not n. So that will not hold. Okay? Now let's look at the graph just to see it more clearly. The n is the red line that goes smoothly, the bottom red line. And then the pure n squared without any terms or without any constants is just the blue line. Okay? Now, if you look at my attempt to make n bigger, so I've plotted here 10n, and I have plotted 100n. And as you noticed, regardless of how much big I can make n by multiplying it by a constant, there will always be a point after which the n squared will take over and will be an upper bound. Okay? So I cannot actually find a constant that I multiplied by n and make it, as we go to infinity, equal to n squared. It has to be another n. And I hope this is clear from algebra. It's just impossible. Okay? But thinking about it asymptotically, because we're really interested in the behavior as we go to infinity, is better illustrated by on the chart. Okay? That regardless of how big your constant that you multiply by n squared will always take over. Okay? After some time. And consequently, since I'm saying that I'd like to find an upper bound for n squared, or I want to find the worst case for n squared, it cannot be n. it has to be n squared or a bigger power, like n to the cube or n to the 4 and so on, because that would be above it on the chart. Okay, so that I can say it will never be worse than n squared. Okay, so let's look at the examples where we try to prove formally that a given term is in some big O. Considering example 3, I have 7n minus 2, and I know intuitively this is O of n, but let's prove it formally. So formally, this means I want to find c and n naught. So if I set the c to 7 and n naught to 1, then I'm really talking about 7n minus 2 being in big O of 7n. And it is actually indeed so, because after 1 on the x-axis, or n naught being 1, the 7n will be above 7n minus 2. So that is proof that 7n minus 2 is in big O of n. The second example, or example 4, 3n cubed plus 20n squared plus 5. So intuitively we know this is in O of n cubed, but let's actually try to prove it. If I would like to say that 3n cubed plus 20n squared plus 5 is in O of n cubed, then I need to find a c after which some variation of n cubed is above this curve we're looking at, 3n cubed plus 20n squared plus 5. Working out the mass, you can see that I will start the mass by saying, okay, so 3n cubed plus 20n squared plus 5 is less than or equal to some constant multiplied by n cubed. I'll do a bit of mathematical manipulation and I will find that if I set my c equal to 4, then after n being 21, or n naught, since n naught is 21, after n being 21, the O of 4n cubed is going to be above this curve. And if you think of it intuitively, of course, when you have 3n cubed, 4n cubed is going to be above it, ultimately. Even though you have an additional term added to the 3n cubed, which is the 20n squared plus 5, ultimately the 4n cubed will be above it. But what we're doing here is that we're proving it formally through mass instead of just by intuition. Now the fifth example is 3 log n plus 5. So this is in O of log n. Now again, I need to find a constant to multiply it by log n, so that that constant multiplied by log n curve is above on the chart, is above 3 log n plus 5 after some n value. Now, doing some logarithmic manipulation here, I will find that my constant is 8. So 8 log n will be above 3 log n plus 5 after 2, or after n equal to 2, because n naught I have found is 2. We will see exactly how do we reach to the c and n naught, but I will just postpone this to a few slides ahead. Now, again, to stress the point, the big O, which you have already been taught that it's the worst case scenario, it is indeed, but we talk about it formally as the upper bound. Okay, we don't talk about it just being worst case, it's the upper bound. Now, the statement f of n is in O of g of n means that the gross rate of f of n is no more than the growth rate of g of n. Okay, so let's look at the table at the bottom to really grasp the relation between them. If g of n grows more, then f of n is in O of g of n. Okay, g of n is not an O of f of n. If I say that g of n, I'm talking about the first row in the table, if I say that g of n grows more or faster than f of n, then f of n cannot be an upper bound to g of n. Okay? The reverse is true. G of n, since it grows faster, it's an upper bound to f of n. Now, if f of n grows more than g of n, then the reverse is true. Okay? g of n is in O of f of n cannot be claimed to be in O of g of n. Okay? Now, the interesting case is the third case, if they are actually the same. If g of n is the same as f of n, then I could claim that f of n is in O of g of n, and I could also claim that g of n is in O of f of n. Okay? Now, going back to the rules that you have learned in your early computer science education, where you're told drop the constants. Now you understand where all this is coming from. Okay? Let me read the bullets. It says if f of n is a polynomial of degree d, then f of n is in O of n to the d. Okay? In other words, I could theoretically come up with any function or any g of n that is above f of n, and I claim it to be an upper bound. Okay? Are you following what I'm saying? If I give you a curve, f of n, some f of n, and I tell you find me something that's above it, there are a huge class or set of classes of curves that are above it. There's not one. Okay? So, for example, 2n is in O of n squared. In other words, the curve n squared will be above, as we go to infinity, 2n. Similarly, n cubed will be above 2n. So saying 2n is in O of n cubed is not wrong, because indeed n cubed is an upper bound to 2n. Similarly, n to the 6, n to the 7, n to the 8, anything that's above n is an upper bound to n. N will never cross it. That's why we call it an upper bound. Okay? But we are going to set a very important rule that we're going to use the smallest possible class of functions. So, saying 2 to the n is in O of n squared is not mathematically incorrect, but it's not what we are after. We are after the smallest class of function that's above 2 to the n, 2n. So that's going to be just n, okay, or some variation of n. Okay? So this is an important distinction between two words, an upper bound and a tight upper bound. A tight upper bound means it's closely above it, as close as possible above it. Just an upper bound, it could be anywhere above it. It could be in the sky. Okay, so that's not what we're after, because that's not accurate. You know, from a computational point of view, it's inaccurate to say, you know, that I can see that the number of steps is 2n, but I'm going to say that the upper bound rate is n to the 7. That's not really helpful. Okay? Mathematically it is correct, but it's not helpful. So we will stick to the smallest possible class of functions, and we will distinguish it by calling it the tight upper bound. Okay? Now, the other rule, which I hope by now you got the idea, I'm going to always use the simplest expression of the class. So I'm not going to say the performance is 3n plus 5. I'm just going to say O of n. Okay? I'm not going to say 7 log n or 73 log n. I'm just going to say log n. Okay? Now, when will this really matter? When does it make a difference between 7 log n and 73 log n? It will make a difference if you're comparing two algorithms that are doing the same task or the same functionality, but they're doing it differently. And both of them belong to the same class. One of them is 7 log n, and the other one is 73 log n. Or one of them is 20n squared, and the other one is 500n squared. Now you start caring about the constant. But for all other purposes, it's enough to say log n or n. Now let's complete the picture by defining two more units, which you haven't seen before. The first one we're going to look at is called the big omega. Now, big omega is the opposite of big O. So I'm going to read the definition and you will see that it's almost a mirror replica with a minor change. We could say that f of n is in omega of g of n if there is a constant c greater than 0 and an integer constant n naught greater than 1 such that f of n is greater than or equal. Before it was the big O, it was less than. Here it's greater than or equal some constant multiplied by g of n. In other words, I'm looking here for the curve that lies below my f of n. In the big O, I was thinking about the curve that will lie on the top of my f of n. Now I'm considering the curve that's below my f of n after some n, which I'm calling it n naught. As we go to infinity, it will always be below it, this g of n. Okay? So if we have talked about big O being the worst case, obviously this is going to be the opposite of that. This is the best case, because we are talking about g of n that is less than f of n. So it's the best thing you can do, okay? Because if you remember from the curve, the y-axis was the number of operations or steps you're going to do. So if you are talking about the curve that's below f of n, then the number of steps is going to be less. So that's actually the best case. The logic still applies. We're going to work out the formula to figure out n naught and c. C is the constant we multiply by our target function class to bring the line below f of n after some n naught. So we need to find, to prove that f of n is in omega of g of n, we need to find c and n naught where that is realized. Now, what if big omega and big O agree on the same term? So you have an algorithm that the big O for it says n squared and the big omega for it is n squared. In that case, you can say that this omega has a theta of n squared. So if the omega and the O agree on the same function class, n squared, n cubed, or n to the 7, or log n, or n log n, if they agree in the worst case and the best case, then you can freely describe the performance as being theta of this function class. Let me read the definition. It says f of n is in theta of g of n if there are constants c naught greater than 0 and c double naught greater than 0 and an integer constant n naught greater than 1, such that, as you see, f of n here is sandwiched between c naught multiplied by g of n and c double naught multiplied also by g of n. Okay? Now, it doesn't mean here that if I say that a curve, or sorry, a piece of code is in theta of log n, that the worst case and the best case will agree exactly in the same log n, variation of log n. So it could be that the worst case is 50 log n and the best case is 3 log n. It's still log n, so I'm going to describe it as being theta of log n. But obviously there will be a difference, a partial, minor difference between the best case and worst case. And that's why here in the formal definition we use two different constants, c naught and c double naught. Okay? Now, if you think about this, you will, if you're wondering, like, are there algorithms that have the worst case and best case the same? And the answer is yes. There are not many of them, but there are. There are, quite a few in almost every area of computer science algorithms. You will find some that have their worst case and best case the same. And in this case, whenever you read about them, you will notice that whoever is describing their performance will tell you this algorithm is in theta of so and so. And obviously, these algorithms are interesting in one aspect, which is that when you work with them, you feel more comfortable because you know exactly what performance you're going to get from this thing, regardless of whether it's good or bad. But because there is an issue with having an algorithm that will have a separate worst case from the best case. For example, an algorithm could be in the worst case n to the 7, and in the best case it's n to the 3. There's a huge difference between n to the 3 and n to the 7, and that makes you worried, because when you're using the algorithm If you hit the worst case, you're talking about n to the 7. That's really slow. Okay? Now, so when you get an algorithm that is always the same asymptotic performance, it's always in some theta, even though if it's like n to the 4, well, at least you know that you always get this consistent performance. Okay? But this is not something that is under our control. If you're forced to use a specific algorithm because you would like to accomplish a certain task, and this is the algorithm that you can put your hand on because there's available implementation, or it comes as part of a library and so on, then you will have to live with whatever performance the algorithm is working according to. But if obviously you have a choice, then you should always go for an algorithm whose worst case and best case is the same. So you have kind of the performance under control, regardless of the data that is being passed. So, to summarize, now you know 3 formal notations that are used to describe the performance of code. Big O, it's an upper bound, big omega, a lower bound, and big theta when big O and big omega agree. Okay? Again, big O means upper bound, which means that the curve that you are putting to say that I am in this asymptotic order means it will always be above your performance curve after some point, and that will continue to infinity. The same thing for the lower bound. The curve that you put below your performance curve, as you go to infinity, after some point it will always be below it. And big theta, I think we've already described that. So let's see this example. If I ask you, prove that 5n squared is in theta of n squared, what you need to prove is that 5n squared is in O of n squared, and 5n squared is in omega of n squared, and consequently you prove that it is in theta of n squared. So the first bullet deals with proving that 5n squared is in O of n squared. What again you need to find is the constant that you multiply by n squared that will make that line above the 5n squared line on the chart. And you need to report the value of n naught, which is the value after which this happens. On a parallel note, you have 5n squared is in omega of n squared. You need again to find the constant and the n naught to prove that it is in omega of n squared. So any curve that is in the variation of n squared that is below 5n squared will work. Okay? So for example, I could use just plain n squared. So c is 1. Okay, and consequently n naught will be 1. Since I have proven that it is in O of n squared and omega of n squared, then consequently it is in theta of n squared. Perhaps it's time to remind you of properties of functions that you have learned, I believe even since your school days. I'm referring to transitivity, reflexivity, symmetry, and complementarity. So let's pick one by one, and I'm just applying information or theory that you have seen before, except now in using the big O and big theta and big omega notation. So if we have that f of n is in theta of g of n, and g of n is in theta of h of n, that implies that f of n is in theta of h of n. Similarly, and this is what we call the transitivity property, if you recall from the school days. Let's read the second line. It says if f of n is in O of g of n, so g of n is an upper bound to f of n, and g of n itself is in O of h of n, then f of n is in O of h of n. Basically, if g of n is an upper bound to f of n, and h of n is an upper bound to g of n, then for sure h of n is also an upper bound to f of n. If you organize the lines on the chart one above the other, for sure way at the top you will see h of n, then g of n, then f of n. And the reverse. If f of n is in omega of g of n, and g of n is in omega of h of n, so f of n must be in omega of h of n. So again, if you organize or draw the lines on the chart here, f of n will become at the top, and then below it g of n, and then below it h of n. Now, reflexivity application to asymptotic orders is stated down in the last 3 lines. F of n is in theta of f of n, f of n is in O of f of n, and f of n is in omega of f of n. Okay? What does that imply? If I tell you, is 5n in n? And the answer is yes. You could prove it formally the same way we have seen before, or you can just tell me because of the reflexivity property. So this is the implication of using these properties. Now for the symmetry property, I can only say that f of n is in theta of g of n if and only if g of n is in theta of f of n. Remember saying that f of n is in theta g of n, for example, to say that 3n is in theta of n, that means n is in theta of 3n. Just like I have found a constant to prove that f of n is in O of n and omega of n, I should be able to find other constants that will make g of n is in theta of f of n. The final property, which involves the complementarity, is that f of n is in O of g of n if and only if g of n is in omega of f of n. If I say that one curve is an upper bound to another, then another way to say it is the one at the bottom is a lower bound, not an upper bound, but a lower bound to the one at the top. Okay? So they are one complement the other. And now let's look at this example, which along with the coming one will kind of involve some thinking into the big O and big omega notation. Let me read it first. It says, is it true that n divided by 100 is in omega of n? So n divided by 100 means 1 over 100 multiplied by n. Okay? Can I claim that a lower bound to this f of n is n? So I'm looking for a curve that is below 1 over by 100 multiplied by n. So for sure I can pick C to be 1 over 200. So 1 over 200n as a curve, if you plot it, it will be below 1 over 100n. Okay? And once I find the C, then I can find the n node. Another example here. This is a little bit more interesting even. Let's say I have two algorithms. Algorithm A is in O of n log n. Algorithm B is in omega of n squared. So the worst case for algorithm A is n log n. Now the best case has to be better than that because this is the worst case. I'm not told what is omega for A. And I'm told that the best case for algorithm B, the omega is n squared. That's the best case. But I'm not told what is its worst case. So obviously the worst case has to be worse than the best case. So it's going to be something worse than n squared. Okay? And that could be anything. It could be n cubed. It could be n to the 4. It could be 2 to the n. Now let me read the second line. It says, therefore, given the same input, A always takes less time to run than B. Is that true or false? Let me read this again. If I provide the same input to A, if it performs in its worst case, it's going to be n log n. And if it performs with that input in its best case, it's going to be something else, I don't know. So it's going to be better than n log n. Now I give this same input to B. If it performs at its best case, it's going to be n squared. But if it performs at its worst case, I don't know. It's going to be something worse than n squared. Okay? So can I claim this? A will always take less time to run than B. Now, the answer is this is false. Why? You see, when we refer to n log n or n squared, I'm referring to the function class. I'm ignoring the constant. But if I ask you a specific algorithm, will it always take less time than another algorithm? Then you have to start thinking of the possible constants that would violate this rule. If you can't find such constants, then it is safe for you to claim that the statement is correct. But if you can find such constant, then you'll have to revise your initial thinking that it is the case and say, no, actually, there is a constant that will make the performance not necessarily better for A. And as you see here highlighted in red, actually, there are such constants, okay? So for example, if the constant multiplied by the n log n is so big and the constant multiplied by n squared is so small, then the picture changes, okay? What you were thinking initially, that yes, the answer is yes, will actually not be true, okay? So what this highlights is two things. First of all, you need the big O and the big omega to completely characterize the performance of an algorithm. Knowing the big O alone or the big omega alone is not enough. The second thing is, when you're comparing two algorithms, you have to start to worry about the constants. We're not really kind of violating everything we agreed on, that we're going to ignore the constants. We ignore them when we talk about a specific algorithm, but when you start to compare algorithms, you have to worry about the constants, because the constants could actually change a little bit of the performance based on the worst and best case values or function classes, as you see in this example. Now let's look at this example, which again will take you into a little bit of thinking about the big O. It says a student has an algorithm which he proved correctly runs in O of 2 to the n. Well, how lucky he is. I mean, that's like a ridiculous performance, okay? He coded the algorithm correctly, yet he was surprised when it ran quickly on inputs of size up to 1 million. And the question is, what are at least two possible explanations of this behavior? How come you know the asymptotic order of an algorithm to be 2 to the n? 2 to the n is a ridiculous number, okay? And a ridiculous performance, basically. And if you actually put the n to be 1 million, that's 2 to the million. So you expect the program to crash or the computer to run out of memory. But actually what's happening here is that the program is running fast. Okay? So here are two possible explanations. 2 to the n is an exponential behavior. Okay? Now, this does not actually manifest itself until n is quite huge. What does that really mean? You see, that student must have calculated the number of steps in his algorithm, and he came up with a term. Perhaps it's a big term, okay, that has many subterms, like, you know, 2 to the something plus n cubed plus n7 plus n squared plus whatever. And when he actually tried to find out the big O using the formal way we have discussed, he reached a conclusion that it is actually 2 to the n. But that doesn't mean that the n node is close to the 0 on the x-axis. It could be way inside the x-axis. Okay? Before it, the performance was not 2 to the n. But the upper bound is 2 to the n as we go to infinity, like we discussed before. And that might not happen or manifest itself or be real except when the n node, for example, crosses 2 million, say. Before that, the performance was going up and down, okay, because of the existence of different pieces in his code that are doing things that makes the performance go up and down. But ultimately, the curve stabilizes after a big n node, and it becomes the upper bound 2 to the n. Okay? Now, the other explanation is that maybe what he passed as input was organized in a way that makes the omega of the algorithm much, much better than 2 to the n. Perhaps the omega is n log n. while the big O is 2 to the n, the best case performance is way better than the worst case performance by magnitudes and magnitudes. And perhaps the input actually was organized in a way so that his algorithm is running actually at its best case. Now we come to the issue of how do we find the CNN node. I have been showing you many examples where I found the CNN node. Okay? And the question is, if I give you a big term that has many subterms, like 17 x to the n to the 5 plus 14 n to the 4 plus 29 n to the 3 plus 50 n squared plus n plus 9. How do you find the n node and the c? There's a number of techniques, so let's look at them. Now, this is what I'm going to do. I'm going to work out the power and coefficients method. Okay, so I'm giving this long polynomial, just like the one I was describing verbally in the previous slide, and I would like to find n node and the c. So what I'm going to do is I'm going to rewrite in step 1 all my terms organized from biggest to smallest as powers of n, and then I will find the larger order by raising to the power to highest value. What does that mean? I'm going to say, okay, this is the term I'm looking for an upper bound for, or a worst case for. So if you think graph-wise, I'm looking for a curve that's above it. So to find that curve easily, I'm going to say the following. This term, n to the 5 plus 5n4 plus 0 to the n3 plus 10n squared plus 5n1 plus 1n plus 1 to the power of n, plus 1 multiplied by n to the 0 must be less than all the n terms raised to 5. So I will pick the highest power and use the same coefficients, the constants, but I will change the powers. So for sure, what's on the left hand side in step 2 is less than what's on the right hand side. Okay? This has to be less than or equal n to the 5 plus 5n to the 5 plus 0n to the 5 plus 10n to the 5 plus 5n to the 5 plus 1n to the 5. Okay? The next step, I'm going to add these coefficients. So the total sum of all of these coefficients has to be 22. It's 1 plus 5 plus 0 plus 10 plus 5 plus 1, so that will be 22. So the left hand side in step number 3 has to be less than or equal to 22n to the 5. So I will work this one to be my c. Okay? This has to be above it, just using simple mathematical rules as you see here. Now what remains knowing my c is to calculate n node, and that's obviously a straightforward a problem. I hope you can easily figure that out. And you will see examples of this in the tutorial. So this is called the power and coefficients method. Okay? You're basically picking the highest power and raising everything to that highest power, the same number of terms I had with the same coefficients, but raised to the power of the highest term. Add it up, and now I got a curve that will be for sure above the polynomial I'm starting with, which is f of n. So my g of n here is going to be 22n to the 5. Now, the next technique where we could use to find n node and c is to divide f of n by g of n. Remember, the definition of big O says that f of n is going to be less than or equal to some constant multiplied by g of n in order to claim that f of n is in O of g of n. So I'm going to treat this just simple, in a mathematical way, in very simple mathematics. I'm going to say, okay, let's divide f of n by g of n. If my claim is true, I should find that the right hand side has some constant. Like the example at the bottom here. F of n is equal to n cubed plus n. How can I prove that this is actually in O of n cubed? Well, I'm going to take n cubed plus n and divide it by n cubed and solve. So this will give me 1 plus n divided by n cubed, which is 1 plus 1 divided by n squared. And now I need to figure out, what will this result in. Okay? So any value, any constant value greater than or equal to 2 will do the job, as you know it's written down there, and consequently n naught is going to be equal to 1. Now the third technique to find the C and the n naught is to use limits. Now here we have three cases for the three variations we could encounter: f of n being in theta of g of n, f of n being in O of g of n, and f of n being in omega of g of n. So let's look first at f of n being in theta of g of n. Now, if I say that it's in theta of g of n, that means it's in O of g of n and it's in omega of g of n. So it cannot be growing faster or slower than g of n because it's sandwiched between g of n. So I could easily say that f of n has the same rate of growth as g of n. So what I'm going to do is I'm going to divide f of n by g of n, and knowing that those two functions have the same rate of growth, if I take the limit as n goes to infinity, I should end up with some constant, which is the factor of difference between the two functions, but it's not a polynomial difference, it's just a constant. And this is what you see as the example at the bottom. If I try to prove that a of n squared plus b of n plus c is in theta of n squared, I'm going to divide that by n squared, and I will apply limits later on. So the limit on the quotient, or the result from the division, is going to be the limit as n goes to infinity of a plus b divided by n plus c divided by n squared. As n goes to infinity, b divided by n will become negligible, they'll be a very, very small value. C divided by n squared will going to be the same, so I'm left with a, which is a constant. Now the way you apply this is the reverse of my explanation. So if I ask you, prove that f of n is in theta of g of n, you divide f of n by g of n and take the limit as n goes to infinity. And if the result of taking the limit is a constant, then you conclude that f of n and g of n must have the same growth rate, and consequently f of n is in theta of g of n. Now the second case, where f of n is in O of g of n, okay? What this means is that f of n is growing slower than g of n. Now if I take the limit, since f of n is growing slower than g of n, the result will converge to 0. So the result will be 0. Okay? Just like the example I have at the bottom here, I have a n squared plus b n plus c divided by n cubed, because I'm trying to prove that is an O of n cubed. Okay? Now you do the division and you take the limit as n goes to infinity. It's going to be a by n plus b by n squared plus c by n cubed. N becomes so huge because it's going towards infinity, so all these terms will be negligible and they will sum up to 0 at the end. Okay? So again, the technique here, you will apply it in the reverse of my explanation. What you will do is, if I tell you prove that f of n is an O of g of n, so you divide f of n by g of n, you take the limit as n goes to infinity, do the division first, and then apply the limits, and then find out if the result is 0. If the result is 0, then f of n is slower than g of n, and it is indeed an O of g of n. Okay? Let's look at this example as an application of all of this. So I have f of n is 4n cubed plus 3n squared, and I would like to prove that it is an O of n to the 4. So I take the limit as n goes to infinity of 4n cubed plus 3n squared divided by n to the 4. And now I start to solve applying regular limit theory. This will fall back to your calculus knowledge. You just take the limit and you will find it's going to be 0, and consequently you have proved that 4n cubed plus 3n squared is an O of n to the 4. Now the third case is that f of n has a larger rate of growth as g of n. So f of n is an omega of g of n. Again, you take the limit of f of n divided by g of n as n goes to infinity, and if the result is infinity, then you have proven that f of n is growing faster than g of n, and consequently f of n is in omega of g of n. Just again like the example you see at the bottom, a of n squared plus b of n plus c, I would like to prove that it is an omega of n. So what I'm going to do is I'm going to take the limit, and it's going to be a to the n plus b plus c divided by n. Okay, so this will amount to infinity because of e to the n. And again, here the application is going to be reverse of my explanation. If I ask you prove that f of n is an omega of g of n, you divide f of n by g of n, you take the limit and it goes to infinity, and if the result is infinity, then you have proven that f of n has larger growth rate, and consequently f of n is an omega of g of n. So what I just described as a name in textbooks, it has been called the limit asymptotic theory. Okay? The limit asymptotic theory say that you divide f of n by g of n, you take the limit as n goes to infinity, and you have the three cases that I have described, and consequently you can draw a conclusion based on the value of the L, which is the result of taking the limit, as I've already explained. Okay? You will see this explained as well in the Corman textbook, so I'm putting a reference to it at the end of the lecture slides. And here are the references for today's lecture. I'm again including the Corman textbook, which is the classical textbook for this course, and I'm giving you also readings from another textbook that I have put for you on the Google Drive, which is Algorithmic Design Manual by Sakina. Pages 31 to 46 are nice to read, nice intro to asymptotic analysis, which we covered in today's lecture. I've also mentioned before in one of the early lectures that you need to sharpen your math skills, or have a memory refresher of the various math skills that you've used and learned early on in your education. So I have put here two references, page 54 to 60 in Corman. There's a math review that we need in the analysis course, and also Appendix A in Goodrich and Tamassia, as well as the summation rules in the Wikipedia page referenced here. I'm going to be using that in the next lecture. And you can always download the textbooks as I have described before.